Quadratic SIEVE. A quadratic SIEVE algorithm (QS) is an integer factorization algorithm and, in practice, the second fastest method known after the general number field SIEVE. It is still the fastest for integers under 100 decimal digits or so, and is considerably simpler than the number field SIEVE. It is a general-purpose factorization algorithm, meaning that its running time depends solely on the size of the integer to be factored, and not on special structure or properties. It was invented by Carl Pomerance in 1981 as an improvement to Schroeppel's linear SIEVE. Basic aim. The algorithm attempts to set up a congruence of squares modulo n the integer to be factorized, which often leads to a factorization of n. The algorithm works in two phases: the data collection phase, where it collects information that may lead to a congruence of squares, and the data processing phase, where it puts all the data it has collected into a matrix and solves it to obtain a congruence of squares. The data collection phase can be easily parallelized to many processors, but the data processing phase requires large amounts of memory, and is difficult to parallelize efficiently over many nodes, or if the processing nodes do not each have enough memory to store the whole matrix. The Bloch-Wiedemann algorithm can be used in the case of a few systems each capable of holding the matrix. The naive approach to finding a congruence of squares is to pick a random number, square it, divide by n, and hope the least non-negative remainder is a perfect square. For example, $80 441 equal 21 p mod $5,959. This approach finds a congruence of squares only rarely for a large n, but when it does find one, more often than not, the congruence is non-trivial and the factorization is complete. This is roughly the basis of Fernet's factorization method. A quadratic SIEVE is a modification of Dixon's factorization method. The general running time required for the quadratic SIEVE to factor an integer n is $E1 plus U \sqrt \ln n ln n equals ln left in the L notation. The constant e is the base of the natural logarithm. The approach to factorize the integer n, Fermat's method entails a search for a single number such that the remainder of a 2 divided by n is a square. But these are hard to find. The quadratic SIEVE consists of computing the remainder of a 2/n for severally, then finding a subset of these whose product is a square. This will yield a congruence of squares. For example, consider attempting to factor the number 1649. We have $41 2 \eq 32, 42 2 \eq 115, 43 2 \eq 200 p mod $1649. None of the integers 32, 115, 200 is a square, but the product 32 200 equals 82 is a square. We also had $32 \c dot 200 \eq 40, 12 c dot 43 2 equal 41 c dot 43 2 \eq 114 2 p mod $1649 since $41 c dot 43 \eq 114 p mod $1649. The observation that 32 200 equals 82 thus gives a congruence of squares. $114 2 \eq 82 p mod $1649. Hence 114 2 minus 82 equals 114 plus 80, 114 minus 80 equals 194, 34 equals k 1649 for some integer k. We can then factor 1649 equals GCD 194, 1649 GCD 34, 1649 equals 9717 using the Euclidean algorithm to calculate the greatest common divisor. So the problem has now been reduced to, given a set of integers, find a subset whose product is a square. By the fundamental theorem of arithmetic, any positive integer can be written uniquely as a product of prime powers. We do this in a vector format. For example, the prime power factorization of 504 is 2332507. It is therefore represented by the exponent vector 3201. Multiplying two integers then corresponds to adding their exponent vectors. A number is a square when its exponent vector is even in every coordinate. For example, the vectors 3201 plus 1001 equal 4202, so 514 is a square. Searching for a square requires knowledge only of the parity of the numbers in the vectors, so it is sufficient to compute these vectors mod 2, 10 over 1 plus 10 over 1 equals 0. So given a set of 1 vectors, we need to find a subset which adds to the 0 vector mod 2. This is a linear algebra problem since the ring letter 2124/2 letter 2124 can be regarded as the Galois fields of order 2, that is, we can divide by all non-zero numbers there is only one, namely 1 when calculating modulo 2. It is a theorem of linear algebra that with more vectors than each vector has entries, a linear dependency always exists. It can be found by Gaussian elimination. However, simply squaring many random numbers mod n produces a very large number of different prime factors, and so very long vectors and a very large matrix. The trick is to look specifically for numbers as such that a 2 mod n has only small prime factors. They are smooth numbers. They are harder to find, but using only smooth numbers keeps the vectors and matrices smaller and more tractable. The quadratic sieve searches for smooth numbers using a technique called sieving, discussed later, from which the algorithm takes its name. The algorithm. To summarize, the basic quadratic sieve algorithm has these main steps. 1. Choose a smoothness bound b. The number pi b, denoting the number of prime numbers less than b, will control both the length of the vectors and the number of vectors needed. 2. Use sieving to locate pi b plus 1 numbers I such that bi equal I2 mod n is b smooth. 3. Factor the bi and generate exponent vectors mod 2 for each one. 4. Use linear algebra to find a subset of these vectors, which add to the 0 vector. Multiply the corresponding I together and give the result mod n the name a. Similarly, multiply the bi together, which yields a b smooth square b2. 5. We are now left with the equality A2 equal b2 mod n, from which we get 2 square roots of a 2 mod n, one by taking the square root in the integers of b2, namely b, and the other they are computed in step 4. 6. We now have the desired identity, $ plus Bobby / equals 0 / p mod n $. Compute the GCD of n with the difference or sum of r and b. This produces a factor, although it may be a trivial factor n or 1. If the factor is trivial, try again with a different linear dependency or different The remainder of this article explains details and extensions of this basic algorithm. The algorithm pseudocode. Algorithm quadratic sieve is choose smoothness band b let t equals pi b for I1, t plus 1 do choose x0, plus or minus 1, plus or minus 2, $I equal x plus \alpha or \sqrtn. Flow $bi equals I2 minus n where $bi equals \prod j equal 1 tpjei j while check pt smooth I equals false do let vi equals vi 1 vi 2 vi t equals ei 1 mod 2 ei 2 mod 2 ei t mod 2 find t1 2 t plus 1 summation I tvi equals 0 let 2124 to let x equals I to I mod n let $y equals \prod j equal 1 tpj \sum I \n teij \b mod n $if $x up \ec of y \b mod n and $x up \ec of y then return gcdxy n gcdx plus y and else return to main loop. How QS optimizes finding congruences. The quadratic sieve attempts to find pairs of integers x and x, where x is a function of x satisfying a much weaker condition than x2 identical to y2 mod n. It selects a set of primes called the factor base, and attempts to find x such that the least absolute remainder of x equal x2 mod n factorizes completely over the factor base. Such y values are said to be smooth with respect to the factor base. The factorization of a value of x that splits over the factor base together with the value of x is known as a relation. The quadratic sieve speeds up the process of finding relations by taking x close to the square root of n. This ensures that x will be smaller and thus have a greater chance of being smooth. $x equals \left left seal \sqrtn int seal plus x I2n \h box where x \h box is a small integer $. $x approx talks \left seal \sqrtn int seal $. This implies that y is in the order of talks. However, it also implies that y grows linearly with x times the square root of n. Another way to increase the chance of smoothness is by simply increasing the size of the factor base. However, it is necessary to find at least one smooth relation more than the number of primes in the factor base to ensure the existence of a linear dependency. Partial relations and cycles. Even if for some relation x is not smooth, it may be possible to merge two of these partial relations to form a full one if the two YS are products of the same primes outside the factor base. For example, if the factor base is 2, 3, 5, 7 and n equal 91, there are partial relations. $20 12 equals 7 1 c.11 p mod 90 $1 $29 equal to 1 c.11 p mod 90 $1. Multiply these together. $21 c.29 equal 1 c.7 1 c.11 p mod 90 $1. And multiply both sides by 11 minus 1 2 modulo 91. 11 minus 1 modulo 91 is 58, so $58 c.21 c.29 equal to 1 c.7 1 p mod 90 $1. $14 2 equal to 1 c.7 1 p mod 90 $1, producing a full relation. Such a full relation obtained by combining partial relations is called a cycle. Sometimes, forming a cycle from two partial relations leads directly to a congruence of squares, but rarely. Checking smoothness by sieving. There are several ways to check for smoothness of the Ys. The most obvious is by trial division, although this increases the running time for the data collection phase. Another method that has some acceptance is the elliptic curve method ECM. In practice, a process called sieving is typically used. If fx is the polynomial fx equals x2 minus n, we have begin at line fx and equals x2n fx plus kp and equals x plus kp to n and equals x2 plus twox plus kp to n and equals fx plus twox plus kp to equiv fx p mod p end line . Thus solving fx identical to 0 mod p for x generates a whole sequence of numbers y for which y equals fx, all of which are divisible by page. This is found in a square root modulo prime, for which there exist efficient algorithms such as the Shanks and N-Nelly algorithm. This is where the quadratic sieve gets its name. Y is a quadratic polynomial in x, and the sieving process works like the sieve of Eratosthenes. The sieve starts by setting every entry in a large array of bytes to 0. For each p, solve the quadratic equation mod p to get two roots alpha and beta, and then add an approximation to log to every entry for which x equals 0 mod p, that is, and it is also necessary to solve the quadratic equation modulo small powers of p in order to recognize numbers divisible by small powers of a factor base prime. At the end of the factor base, any containing a value above a threshold of roughly log x2 minus n will correspond to a value of x which splits over the factor base. The information about exactly which primes divide x has been lost, but it has only small factors, and there are many good algorithms for factoring a number known to have only small factors, such as trial division by small primes, Skofov, Polodrer, and Eckham, which are usually used in some combination. There are many x values that work, so the factorization process at the end doesn't have to be entirely reliable. Often the processes must behave on say 5% of inputs, requiring a small amount of extra sieving. Example of basic sieve. This example will demonstrate standard quadratic sieve without logarithm optimizations or prime powers. Let the number to be factored north equal 15,347, therefore the ceiling of the square root of north is 124. Since north is small, the basic polynomial is an f, x equal x plus 124 2 minus 15,347. Data collection. Since north is small, only 4 primes are necessary. The first 4 primes p for which 15,347 has a square root mod p are 2, 17, 23, and 29. In other words, 15,347 is a quadratic residue modulo each of these primes. These primes will be the basis for sieving. Now we construct our sieve x of $yx equal x plus /LCO /SQRTN. CL2 north equal x plus 124 2 minus 15,347 and begin the sieving process for each prime in the basis. choosing to sieve the first 0 less or equal to x100 of yx. $\begin align v and equals begin b matrix at 0 and urn and itwo and ithri and ifr and ifiv and c dots and unentinine and b matrix and equals begin b matrix 29 and 278 and 529 and 782 and 1037 and 1294 and c dots and 34,382 and b matrix n align . The next step is to perform the sieve. For each p in our factor base 2, 17, 23, 29 solve the equation. $wide x equiv x plus lco sqrdn seal 2 in equiv 0 p mod p $. To find the entries in the array v which are divisible by p. For p equals to solve $x plus 124 to 15,347 equiv 0 p mod $2 to get the solution $x equiv sqrt 15,347 minus 124 equiv 1 p mod $. Thus, starting at x equals 1 and incrementing by 2, each entry will be divisible by 2. Dividing each of those entries by 2 yields $v equals begin b matrix 29 and 139 and 529 and 391 and 1037 and 647 and c dots and 17,191 and b matrix $. Similarly, for the remaining primes p in 17, 23, 29, the equation $x equiv sqrt 15,347 124 p mod p $ is solved. Note that for every p2 there will be 2 resulting linear equations due to there being 2 modular square roots. Begin align x and equiv sqrt 15,347 124 and equiv 8 124 and equiv 3 p mod 17 and equiv 9 124 and equiv 4 p mod 17 x and equiv sqrt 15,347 124 and equiv 11 124 and equiv 2 p mod 23 and equiv 12 124 and equiv 3 p mod 23 x and equiv sqrt 15,347 124 and equiv 8 124 and equiv 0 p mod 29 and equiv 21 124 and equiv 13 p mod 29 end align. Each equation $x equiv p mod p $ results in vx being divisible by p at x equals a and each pth value beyond that. Dividing v by p at a plus p, a plus twop, a plus streep, etc. for each prime in the basis finds the smooth numbers which are products of unique primes first powers. $v equals begin b matrix 1 and 139 and 23 and 1 and 61 and 647 and c dots and 17,191 n b matrix $. Any entry of v that equals 1 corresponds to a smooth number. Since v, and v equal 1, this corresponds to x plus 124 y factors 124 29 20 17 0 23 0 29 1 127 782 2 1 17 123 129 0 195 22,678 2 1 17 123 129. Matrix processing. Since smooth numbers y have been found with property $y equals c2 p mod n $, the remainder of the algorithm follows equivalently to any other variation of Dixon's factorization method. Write in the exponents of the product of a subset of the equations. Begin align 29 and equals T0 backslash C dot 17 0 backslash C dot 23 0 backslash C dot 29 1 backslash 782 and equals to 1 backslash C dot 17 1 backslash C dot 23 1 backslash C dot 29 0 backslash 22,678 and equals to 1 backslash C dot 17 1 backslash C dot 23 1 backslash C dot 29 1 backslash end line. As a matrix, $P mod $2 yields S backslash C dot backslash begin B matrix 0 and 0 and 0 and 1 backslash 1 and 1 and 1 and 0 backslash 1 and 1 and 1 and 1 backslash end B matrix backslash echo backslash begin B matrix 0 and 0 and 0 and 0 backslash end B matrix backslash P mod 2. A solution to the equation is given by the left null space, simply $S equals backslash begin B matrix 1 and 1 backslash end B matrix $. Thus the product of all three equations yields a square mod n. 29,782 22,678 equals 22,678 2 and 124 to 127 to 195 2 equals 3,070,862. So the algorithm found $22,678 to backslash echo of 3,070,862 backslash P mod $15,347. Testing the result yields GCD 3,070,860 22,678 15,347 equal 103, a non-trivial factor of 15,347, the other being 149. This demonstration should also serve to show that the quadratic sieve is only appropriate when n is large. For a number as small as 15,347, this algorithm is overkill. Trial division or Paul Audra could have found a factor with much less computation. Multiple polynomials. In practice, many different polynomials are used for y, since only one polynomial will not typically provide enough x. Y pairs that are smooth over the factor base. The polynomials used must have a special form, since they need to be squares modulo n. The polynomials must all have a similar form to the original y. X equal x2 minus n. X equals x plus b2 minus n, b letter 2124. Assuming b2 minus n is a multiple of a, so that b2 minus n equals c, the polynomial x can be written as x equals x2 plus 2bx plus c. If it is a square, then only the factor x2 plus 2bx plus c has to be considered. This approach, called MPQS, multiple polynomial quadratic sieve, is ideally suited for parallelization, since each processor involved in the factorization can be given n, the factor base, and a collection of polynomials, and it will have no need to communicate with the central processor until it is finished with its polynomials. One large prime. If, after dividing by all the factors less than a, the remaining part of the number, the cofactor, is less than a 2, then this cofactor must be prime. In effect, it can be added to the factor base by sorting the list of relations into order by cofactor. If y a equals 7 asterisk 11 asterisk 23 asterisk 137 and y b equal 3 asterisk 5 asterisk 7 asterisk 137, then y I b equal 3 asterisk 5 asterisk 11 asterisk 23 asterisk 72 asterisk 137 2. This works by reducing the threshold of entries in the sieving array above which a full factorization is performed. More large primes. Reducing the threshold even further, and using an effective process for factoring x values into products of even relatively large primes, ACM is about for this can find relations with most of their factors in the factor base, but with 2 or even 3 larger primes. Cycle finding then allows combining a set of relations sharing several primes into a single relation. Parameters from realistic example. To illustrate typical parameter choices for a realistic example on a real implementation, including the multiple polynomial and large prime optimizations, the tool MSIEVE was run on a 267-bit summa prime, producing the following parameters: trial factoring cutoff, 27-bit sieve interval per polynomial, 393,216 12 blocks of size 32,768 with this bound, 1,300,000. 967,50,294 primes. Number of factors for polynomial coefficients 10c. Multiple polynomials above large prime bound 128,795,733. 26 bits. C. Large primes above smooth values found 25,952 by sieving directly, 24,462 by combining numbers with large primes. Final matrix size 50,294 times 50,414, reduced by filtering to 35,750 times 35,862. Non-trivial dependencies found 15. Total time on at 1.6 GHz Ultra Spark Roman 3, 35 minutes 39 seconds. Maximum memory used 8 MB. Factoring records. Until the discovery of the number field SIEVE, NFS, QS was the asymptotically fastest known general-purpose factoring algorithm. Now, Lenstra elliptic curve factorization has the same asymptotic running time as QS in the case where n has exactly two prime factors of equal size, but in practice, QS is faster since it uses single precision operations instead of the multi-precision operations used by the elliptic curve method. On April 2, 1994, the factorization of RS Aminas 129 was completed using QS. It was a 129-digit number, the product of two large primes, one of 64 digits and the other of 65. The factor base for this factorization contained 524,339 primes. The data collection phase took 5,000 MIPS years, done in distributed fashion over the internet. The data collected totaled 2 GB. The data processing phase took 45 IOs on Belco's Natacordi Technologies Mass Power Massive E parallel supercomputer. This was the largest published factorization by a general-purpose algorithm until NFS was used to factor RS Aminas 130, completed April 10, 1996. All RSA numbers factored since then have been factored using NFS. The current QS factorization record is the 140-digit 463-bit RS Aminas 140, which was factored by Patrick Conser in June 2020 using approximately 6,000 co-IOs over 6 days. Implementations. PPMPQS and P6MPQS SIMPX is a fast implementation of the self-initializing multiple polynomial quadratic sieve written by William Hott. It provides support for the large prime variant and uses Jason Papadopoulos block lengths as code for the linear algebra stage. SIMPX is accessible as the QSIV command in the Sage Math computer algebra package or can be downloaded in source form. SIMPX is optimized for use on Athlon and Octane machines, but will operate on most common 32 and 64-bit architectures. It is written entirely in Celsius. A factoring applet by Dario Alpern that uses the quadratic sieve if certain conditions are met. The Pi/GP computer algebra package includes an implementation of the self-initializing multiple polynomial quadratic sieve implementing the large prime variant. It was adapted by Thomas Papanicolaou and Xavier Roblot from a sieve written for the LIDIA project. The self-initialization scheme is based on an idea from the thesis of Thomas Sosnowski. A variant of the quadratic sieve is available in the Magma computer algebra package. It is based on an implementation of Origin Lenstra from 1995 used in his factoring by email program. MSIEVE, an implementation of the multiple polynomial quadratic sieve with support for single and double large primes, written by Jason Papadopoulos. Source code and a Windows binary are available. Yahoo, written by Ben Burrow, is similar to MSIEVE but is faster for most modern processors. It uses Jason Papadopoulos block length source code. Source code and binaries for Windows and Linux are available. Arial, a simple Java implementation of the quadratic sieve for didactic purposes. The Java math library contains probably the fastest quadratic sieve written in Java, the successor of 6.4.0. Java QS, an open-source Java project containing basic implementation of QS. Released February 4, 2016 by Illa Gazman. Celsius Quadratic Sieve, a factorizer written entirely in Celsius containing implementation of self-initializing quadratic sieve. The project is mathematically inspired by a William Hott lint factorizer. The source, released in 2022 by Mitchell Leonard, does not rely on external library. It is capable of factoring 220-bit numbers in a minute. The RCPP Big Int Algos package by Joseph Ward, provides an efficient implementation of the multiple polynomial quadratic SIEVE for the R programming language. It is written in C++ and is capable of comfortably factoring 100-digit summa primes. For example, our SMOOTHNESS 100 was factored in under 16 hours on a 2.8 GHz quad-core Intel Core i7 personal computer. Other external links. Reference paper The Quadratic SIEVE Factoring Algorithm by Eric Landquist. Category: Integer Factorization Algorithms.